In this section, we're going to learn the methodology for writing and balancing chemical equations. And we're going to do that for both molecular, ionic, and net ionic formats. Balancing chemical reaction equations is done by putting whole number stoichiometric coefficients in front of the chemical formulas for the different reactants and products. Here in this combustion reaction, you can see I have a 38, a 25, and a 26 out in front of these three molecules. It is implied that I have a 1 out here in front of this organic molecule with 25 carbons and 52 hydrogens. We just don't put it in there. We call these numbers in front of these molecules, again, stoichiometric coefficients. These coefficients represent the relative numbers of reactants and products, and these are typically referred to mole quantities. These coefficients can be correctly interpreted, however, as ratios of the different molecules. The coefficients are used to balance a chemical reaction. What that means is I need to have the same number of atoms on the left-hand side as on the right-hand side. So if I look at this combustion reaction, notice I have 25 carbons on the left. I better have 25 carbons on the right. I have 52 hydrogens on the left. I better have 52 hydrogens on the right. 26 times 2. Oxygen's a little more difficult because on the left-hand side I have them all in one molecule. In this case I have 76 oxygen atoms. On the right-hand side I have 50 oxygen atoms here, and I have 26 here. Together those add up to 76. So in fact, this is a balanced chemical reaction. The same number of atoms on the left as on the right-hand side of my chemical reaction. Let's go through the methodology because some chemical reactions are a little more complicated, but we're first going to look at a simpler version of a combustion reaction where I take one of the simplest organic molecules, methane, react it with oxygen to form CO2 and water. So if I look at this chemical reaction, I have methane reacting with oxygen to form CO2 and water. I've depicted that here. In this case, notice that I need 2 oxygen molecules to react with 1 methane molecule. My result is that I get 1 CO2 molecule and 2 water molecules. And that would be my coefficients, 1 to 2 to 1 to 2. But we know we have more than just 2 oxygen molecules and 1 methane molecule typically in a chemical reaction. So in my beaker, I have more oxygen and more methane. Those two will react under these conditions to form more water and more CO2. Notice here, if I add those all up together, I'm now starting with 2 methane molecules, but I need 4 oxygen molecules. And my reactants are going to be 2 CO2 now, this molecule and this molecule, and I'm going to get 4 water molecules. Let's put some more methane and oxygen in our reaction vessel. In this case, I've added 2 more oxygens and 1 methane molecule. They also react to form water and CO2, and it looks like they're reacting in the same ratios. In fact, if I look at that, if I start with 3 methanes, I need 6 waters, and it produces 3 CO2s and 6 water molecules. Regardless of the absolute number of molecules involved, the ratio between the number of molecules are the same as that given in the chemical reaction equation. 1 methane reacts with 2 oxygens to form 1 CO2 and 2 waters. This is the law of definite proportions, and that's what leads to a balanced chemical reaction equation. Let's review that again, but without all the little extra oxygens and methane. So here's my chemical reaction. Methane plus 2 oxygen molecules leads to 1 carbon dioxide molecule and 2 water molecules. Again, this is my reactant side, and this is my product side. Let's formally add up all the atoms now to make sure all the atoms in each of the molecules is represented. Here I have in methane 1 carbon, 4 hydrogens. How many carbons do I have on the right hand side? I have 1 carbon, and 2 times 2, I have 4 hydrogens. On the left hand side, my reactants, I have 4 oxygens. If I go over to my right hand side, I have 2 oxygens in CO2, and I have 2 oxygens in these 2 water molecules, so I can add them all up, and in fact they do balance. I have the same number of atoms on the left hand side as I do on the right hand side. For more complicated balancing equations, I have a methodology that we often use for molecular chemical equations, those meaning covalent bonds. Let's now review that. Here I have a very simple chemical reaction. I have water. It's decomposing to form 2 hydrogens and 2 oxygens. One way to balance it is just by inspection, just sort of trial and error and working through it. So I have 2 hydrogens, 1 oxygen. I have 2 hydrogens on the right hand side and 2 oxygens. That is an unbalanced chemical reaction. To achieve balancing, we need to add coefficients in front of the equation molecules as needed. So let's balance oxygen by adding a 2 out in front of the water, because I need to have 2 oxygens on the left hand side. So I put a 2 out there, remembering now that that gives me 4 hydrogens also. So I have 4 hydrogens, 2 oxygens on the reactant side. I have 2 hydrogens and 2 oxygens on the product side. My oxygens are balanced, but now my hydrogen's out. So now I'm going to actually balance the hydrogens by adding another coefficient out in front of the hydrogen on the product side. So I add a 2 out there, and that only affects hydrogens. So now I look at this chemical reaction. I have 4 hydrogens on the left, 2 times 2. I have 2 oxygens on the left, 2 times O. I have 2 hydrogens on the right-hand side, 2 times 2, and 2 oxygens in my oxygen molecule. This is a balanced chemical reaction equation. More complex chemical reaction equations actually require a better methodology than just trying these numbers in until it works. Let's go through that methodology now using a more complex combustion reaction. Let's use this combustion reaction where I'm actually looking at wax burning again to actually go through the methodology of balancing a complex molecular chemical reaction. I start off with my wax, which has 25 carbons and 52 hydrogens. I react it with oxygen to form CO2 and water. I look at this chemical reaction. I have 25 carbons on the reactant side. I have 1 carbon on the product side. I know it is not balanced. The methodology that we use is to balance the highest molecular weight element in the most complex molecule first. So my most complex molecule is the one with the largest number of atoms. So I'm going to actually balance carbon first. So I have 25 carbons on the left. I need to have 25 carbons on the right. And here I have 1 all by itself, so I just put a 25 out in front of there. Okay. The second step now is because all my other atoms now have been adjusted because I put this 25 out there. I need to balance the other elements in the most complex molecule. The C25H52 is still my most complex. The next element would be hydrogen. So I have 52 hydrogens on the left. I need to get 52 on the right. So I put the 26 coefficient out in front of water. Okay? And then I need to balance all the other elements in the other molecules. I need to balance oxygen in O2, in CO2, and water, because there are 3 different molecules that contain oxygen. Notice one here only contains oxygen, so I literally can add up the oxygens on the left and then just add the coefficient onto here over on the reactant side to make it work out. So here I have, again, 50 oxygen atoms. Here I have 26 for a total of 76. I put a 38 out in front of the oxygen. 38 times 2 is 76. And I only affect oxygen in this case, balancing the chemical equation. In addition to balancing our chemical reaction equation, we often want to indicate the actual states of the different molecules, either a gas, liquid, solid, or aqueous, and we're going to use these parenthetical abbreviations at the end. I know that my wax is a solid at room temperature, so I put an S there. Oxygen is a gas at room temperature, so I put a G. CO2 is a gas, and water is a gas. In addition, if there are any special conditions necessary, we want to add those either in writing or in symbols above the reaction arrow. For example, in this case, this delta, the Greek letter, actually indicates that it either started out by heating this chemical reaction or using an ignition source for this chemical reaction. And there are many different symbols and many different words that we use here depending on what the chemical reaction is. Let's do another example, and let's do a combustion reaction again. In this case, we're going to look at ethane burning, which is one of the chemical components of propane and natural gas. So in this case, I have a hydrocarbon, which has 2 carbons and 6 hydrogens reacting with oxygen, forming H2O and CO2. We're going to start with the most complex molecule and look at the highest molecular weight element, which is carbon. I got 2 on the left. I need to put a 2 out in front of CO2 on the right to balance carbon. Then I'm going to look at hydrogen. I have 6 over on the left. I can add a 3 out in front of there to balance the hydrogens. Now all I need to do is balance the oxygens. And in this case, it becomes a little more complicated. Okay, so I'm going to look at how many oxygens I have on the right-hand side. Let's see, I have 3 here plus 4 here. That is 7. I need to put a 7 out in front of my oxygen here. However, if I put a 7 or a 3.5 out there, it's not a whole number. So I put 7 halves there. And notice now it actually balances. However, in a separate step, we're going to sort of correct this fraction here because we don't like to see fractions. We like to see whole numbers, integers in front of our coefficient. So we're literally going to take that equation that we've balanced. We have 1 mole of ethane. We have 7 halves of a mole of oxygen. We have 3 moles of water and 2 moles of CO2. We're just going to multiply everything by 2. So I got 2 moles of ethane now reacting with 7 moles of oxygen to give me 6 moles of water and 4 moles of CO2. Now it's balanced, and I actually have whole number coefficients out in front. I have integers. We're then going to put down the physical states like we did last time. Gas for ethane, gas for oxygen, gas for water, and gas for CO2. And then any special conditions, we're going to designate those by writing either a word or a symbol above our reaction arrow. In this case, I'm going to put the delta in there again. How about balancing ionic chemical reactions? Those are different. Let's take a look at how we do those. Balancing ionic reaction equations. And let's look at the methodology. The first thing we do is write down the complete molecular equation using the correct formulas of the reactants and products. Here I have sodium phosphate, magnesium chloride, forming magnesium phosphate and sodium chloride. Notice that my atoms do not balance here. I have 3 sodiums on my left, I have 1 sodium on my right. Now I could balance this by inspection by just trial and error, but it becomes difficult. So what we'd rather do in this case, we want to count each element in the reactants and products. So I write them down, and I write them as ions, because I know these are all aqueous ions, so it's an ionic equation, so they will dissociate in water, or they will precipitate, one of the two. So here we go. I count my reactants. I have 3 sodiums on my reactants, 1 sodium on my product. I have 1 phosphate, I have 2 phosphates. I have 1 magnesium, I have 3 magnesium. I have 2 chlorines and 1 chlorine. Those are not balanced. So we're going to start by changing these coefficients on one side or the other until they balance. The methodology that we use is to balance the ions on the left-hand side of the reaction equation first. So I have 3 sodiums, and I have 1 here. Let's leave that alone. On this side, I only had 1, so I'm going to actually add a 2 out so that they're balanced. And on this side, magnesium, I only had 1, but now I'm going to add a 3. Okay? And again, the chlorine, I have more than enough, so I'm going to leave that unbalanced for now. So then I fill in all my chemical reactions and see what I've changed, because I change things as I add a 2 out in front of this larger ionic equation because I affect the phosphates. So now let's record the effect that these coefficients had on the other ions on the left-hand side. So when I added a 2 out in front of the phosphate, I also added a 2 out in front of the sodium. So now I have 6 sodiums. When I added a 3 out in front of the magnesium chloride, I actually now have 6 chlorines there too. 3 times 6. So I changed all those. Notice now I'm balanced in the center, but not balanced here. Now I'm going to look to the product side to fix those values because I have sodiums and chlorines that are alone here. So when I do that, I just add a 6 out in front of the sodium, and I add a 6 out in front of the chlorine, and that's shown here in blue. And then I add all those up. All of my atoms are now balanced, which means all of the atoms in my molecules are balanced. Okay, so I have 2 sodiums here times 3. It gives me 6. I have 6 sodiums on the right-hand side. I have 2 phosphates. Here I have 2 phosphates on the product side. I have 3 magnesiums on the reactant side. I have 3 magnesiums on the product. I have 6 chlorines and 6 chlorines. I have a balanced chemical reaction. Many of the compounds have a suffix AQ on them. That means they dissociate into ions in water. And in fact, we can use that to actually simplify our chemical reaction. This would represent the full molecular reaction, but we could simplify this as an ionic chemical reaction. Let's look at the different levels that we use to represent aqueous ionic chemical reactions. Whenever ions are involved, the chemical equations can be written at different levels of detail. For example, I have my chemical formula here in this chemical reaction. I have calcium chloride reacting with silver nitrate to form calcium nitrate and silver chloride. Notice this is not balanced. I go through the methodology of balancing it all, and I find out that I need 2 of these silver nitrate molecules, and I need 2 of the silver chloride molecules. Now this is balanced. Okay. When I put this materials into water, they tend to dissociate in water to form distinct ions. So I can sort of separate them out. My calcium chloride in water forms calcium and chloride. Okay. My silver forms silver and nitrate ions. My calcium nitrate forms calcium and nitrate ions. Notice that I didn't have in here silver chloride. That's because there's an S here. That's actually a solid that precipitates out a solution, so it does not form ions. So you can see why these parenthetical suffixes are so important when I'm writing an ionic equation, because this does not ionize in water. It remains as a compound and it precipitates out. It does not dissolve in water. The fourth type of ionic equation is actually a complete ionic equation, where I take all my individual ions on the left-hand side and I add them all up into one big equation. So you can see here I have calcium, chlorine, silver, nitrate, my reaction arrow, calcium, nitrate, and silver chloride, my solid. If I look closely, there are several species that are present on both sides of the arrow. I have one calcium on the left, I have a calcium on the right. So did calcium go to make calcium? Sure, it forms ions. I also have the nitrate on both sides. I have NO3 here and NO3 here. I have two of them. They're both aqueous. We call these actually spectator ions because they do not react in this chemical reaction. They just dissociate into ions. So they largely just remain their charge neutrality, and they neither form physical nor process changes, so no chemical reaction. So what I can do is I can take my complete ionic formula now and sort of eliminate the calciums from both sides, eliminate the nitrates from both sides, and then rewrite my chemical reaction equation as a net ionic equation. That is where I take the two ions on the left, they react to form my compound on the right, my solid compound that is not soluble in water, that is not ionic in water. Let's do a second example and determine all the different levels of ionic equations. The first thing I'm going to do for this reaction is write out the chemical formulas in an unbalanced. So I have sodium sulfate reacting with barium hydroxide to form sodium hydroxide and barium sulfate. I go then through the ionic methodology to balance that chemical reaction. It turns out that I just need to add a 2 coefficient in front of the sodium hydroxide, and it is balanced. And then I need, for the next level, I'm going to actually write out the ionic components. So I know sodium sulfate is aqueous. I know that barium hydroxide is aqueous. I know that sodium hydroxide is aqueous. So those three compounds will dissociate into their ions in water. Barium sulfate is a solid, and it will not, as stated down here on the bottom. So let's write out the ionic equations for each of those components. Sodium sulfate dissociates into sodium and sulfate. Barium hydroxide dissociates into barium and hydroxide. Sodium hydroxide into sodium and hydroxide. Notice I sort of kept and added a coefficient in front of some of these to make sure that I have it balanced also, because I need 2 sodiums here because I started off 2 sodiums there. Also notice I sort of keep the charges involved in these ones too. So I need to include the charge and the states. In this case, they're all aqueous. Let's now go ahead into a complete ionic equation. So I have sodium, sulfate, barium hydroxide forming sodium hydroxide and barium sulfate. I'm now going to form the net ionic equation by eliminating all my spectator ions. I look on both sides. I notice I have sodiums on both sides. Cross those off. I notice I have hydroxides on both sides. Cross those off. And by doing that, I come up with a net ionic equation. It's those species that actually react to form a new compound. Barium reacts with sulfate to form barium sulfate. The sodium and hydroxide are just in there as spectators.